So chapter 26 from the title is convective mass transfer. So we closed the discussion of diffusive mass transfer. The last one was chapter 25, where we discussed unsteady state molecular diffusion. And we discussed it, as you remember, for semi-infinite medium and for finite medium. So from here onward, you will start seeing the convective mass transfer. You have seen it in chapter 24 and also towards the end of chapter 25, where we starting or we discussed briefly the boundary layer in chapter 24, or the film theory. And also we mentioned Kc as part of the or as part of finding m, because m in chapter 25 was dAb over Kc times x1, and Kc is the convective mass transfer. So now the focus will be mainly on convective mass transfer, and you will see a lot Kc. This one is the one we discussed briefly before in chapter 24 and 25. Before that, let's define the convective mass transfer. What is it? It is a transfer of a component between two phases. What we discussed in chapter 22 up to chapter 25. At the end of chapter 25, we also discussed between two phases. When we started the charts, discussion of the charts. But before that, we were discussing only in one phase. Okay, diffusion in gas phase, or diffusion in liquid phase, or fluxes in just gas phase or liquid phase. So we didn't discuss between two phases. Even the example we started chapter 24 with was just, we said that the liquid A is, or the gas doesn't dissolve in liquid A, so still pure A, and then it evaporates, and the transfer takes place only in the gas phase, not in the liquid phase. So from here onward, we will be discussing between two phases. And when we say two phases, we're saying about, for example, between gas and liquid, or liquid and solid, or gas and solid, or maybe two liquids that are immiscible, so they don't mix. So it is a transfer between two phases that is promoted by what? By motion of the fluid phase. If you remember in chapter 22, we said we have two components for flux, or two, the equations, the general equation for the flux comprise two terms. The first one was the diffusion contribution, and the second one was the convective contribution. So it was Na, for example, minus dabc times dya over dz plus the sum ya times the summation of the fluxes, and the second term plus ya summation of the fluxes is the convective term there. So now, if we want just to calculate the flux based on convection, okay, the flux just based on convection, if we know that we have just convection process, then the flux will be Kc, which is convective mass transfer coefficient, times the concentration gradient. Of course, the concentration gradient should be there, otherwise there will be no mass transfer. And if we know that the concentration gradient is like this, CAS minus CA infinity, where CA infinity is the CA infinity is the concentration of A in the bulk fluid, far away from the interface, or we call it the sink for A, or could be the source, depending on where the flux direction, okay, or what is the flux direction. And we have CAS is the concentration of A at the interface, or this is, we call it the source, if the mass transfer takes place from the object toward, or from this surface or this object towards the other surface or other medium. So now, if you remember dAb, the unit of dAb was length square per time. But what do you think the unit of Kc should be? What is the unit of Kc? Depend based on this question here. What is the unit of concentration?
Mole per volume.
Yes. And what is the unit of flux?
Mole per area per time.
So what should be this one?
Meter per time.
Should be meter per length per time, right? To have this one, so when you have meter or unit length per unit length cube, then the cube will become square and this will cancel, and it will be, for example, mole per length square per time, same as the flux. So it has a unit of length per time, while the diffusion coefficient has a unit of length square per time. Okay,
Doctor?
I'm not sure. Yes.
Is this equation before? Did we reach to this equation before?
This one?
Yes.
No, this we didn't discuss this one before. This is the first question in this section. So we have two sections in this book or in this course. The first one is diffusion. The second one is convection. So this, the first thing, probably I mentioned it somewhere there in chapter 24. Yes, we mentioned it in chapter 24, but we didn't discuss it in detail. The objective was just to relate Kc to diffusion coefficient at that point. Okay.
Yes.
Yes, we mentioned in chapter 24. If we go back to chapter 24, we'll find this equation. But the objective was there just to relate Kc to dA. So now I'm sure if you are taking the CHE 300, right? Or maybe finished it already. Right?
Yes,
Yes, we're taking it.
Okay, so is this equation similar in terms of the or analog to this one? This is the convective heat transfer coefficient. Yes, this is the flux, the heat flux basically, which is Q over the area. This is the flux, and H is analog to Kc. This is convective mass transfer coefficient. This is convective heat transfer coefficient, and this is the gradient force, or here the gradient force in terms of concentration. This is the gradient force in terms of temperature. So in this chapter you will, and also in chapter 28, mainly in this chapter, a little bit in chapter 28, you will see some analogy between heat transfer and mass transfer, and even some dimensionless number they can be used, or they are analog to each other in mass and heat transfer. Okay, in convective mass transfer, we'll be discussing two scenarios. The first one is the mass transfer between two immiscible fluids. Basically, we'll not discuss these two, but this is what you will see. Two immiscible fluid phases in contact. So we have A, which is the solute, which is soluble in one of these two phases. For example, you have both liquid and gas, and A, for example, soluble in the gas phase and then transfers into the liquid phase. So we have two immiscible fluid phases in contact where A transfers from one phase to another. So this is one scenario that we have convective mass transfer, and we have to know or evaluate the convective mass transfer coefficient Kc. The second scenario is between solid surface and fluid contacting the solid surface. So we have two fluids here, the two fluids, but should be immiscible. What immiscible mean? What does immiscible mean?
Not soluble and not mixed with each other.
Yeah, they don't mix. They don't mix, okay? So these two immiscible fluids can be just two liquids, like for example, water and oil. They don't mix, water and oil, or maybe gas and liquid. Either gas and liquid, and the gas is insoluble in the liquid, and the liquid is not volatile. So the two phases, gas and liquid, don't mix. So we call them immiscible, or two liquids that are also immiscible, so they don't mix. So this is the scenario, the first scenario. The second scenario, the solid and fluid, and also solid and fluid don't mix. So the fluid can be liquid or gas, and the solid surface, it's so the fluid contacting the solid surface, and mass transfer may take place from solid to the fluid or from the fluid to the solid. So for the first case here, two immiscible fluids, fluid phases, they will be covered in more details in chapter 27. We'll discuss mass transfer between phases. We will call it interface convective mass transfer in chapter 27. So this will be covered, this scenario will be covered in more detail in chapter 27. And there we will discuss it for gas and liquid contact. So our focus will be on this. So gas liquid contact will be covered in chapter 27. The application of this phenomenon is absorption, and absorption is the transfer or the removal of a solute from the gas into a liquid phase. Okay, like this, for example, you have a solute in the gas phase and you don't want it to be in the gas phase, so you want to purify, for example, the gas. Okay, let's say you have a gas, natural gas, for example, and there's, for example, CO2 or hydrogen sulfide in the gas, and we don't want CO2 or hydrogen sulfide in the gas, so we want to make it pure. So we use a process called absorption to remove or to absorb the harmful gases in the natural gas into a liquid. The second process that depends on gas liquid contact is stripping, and this is opposite to absorption. So the mass transfer will take place from liquid into gas phase. And the third one is if you have a mixture of solid and liquid, and you want to dry the liquid, so you want to dry the solid, so you want to remove the liquid from the solid, you do evaporation. So you convert liquid into vapor, which disappears from the solid, and the solid becomes the solid becomes dry. So these are based on gas liquid contacts. Okay, the last one, evaporation, here is also including solid as well. Okay. For this liquid contact, the application is called liquid extraction. So in this case, we have mass transfer from this liquid phase to another liquid phase, or maybe the other way. So this will be covered in chapter 27. This will not be covered in this course, but will be covered in CHE 306 in terms of design. This will be also covered in CHE 306, absorption and stripping, but in terms of design. For this process here, if you have the mass transfer takes place from solid to fluid, we call it leaching, or if it is from fluid to solid, we call it adsorption. This will not be covered in this course, and also not covered in 306. There's an elective elective separation course where this kind of process covered. Okay, adsorption there is covered there. Okay, so this is for two phases, two immiscible fluid phases, gas or liquid. This one you can also replace it with another liquid that is immiscible with the first liquid here, and you still have analog between the process here and whether it's gas or liquid. Sorry. And for the second, when you have fluid contacting a solid surface, you will have this, for example, the fluid flow, and this is the solid. And let's assume that the solid is porous, because if it is not porous and the solute doesn't dissolve in the solid, then you will have no mass transfer inside. So let's say this porous solid, and the mass transfer here mainly takes place by diffusion, molecular diffusion. And in this layer here, which we'll call it later on the boundary layer, or sometimes we call it in chapter 4 the stagnant layer, or if you want to call it based on fluid mechanics, it's called hydrodynamic boundary layer. So you have here, this is the bulk of the gas or the fluid phase, where the concentration everywhere is the same. This phase is very well mixed. So whatever the location, whether you are here or anywhere, this phase or this fluid is very well mixed. So there's no concentration gradient here. Then you have this film from Z0 to Z equal alpha. This is the hydrodynamic boundary layer, or the concentration, we'll call it later on the concentration boundary layer. where you have concentration gradient. So the concentration decreases until it reaches here. This will be the minimum concentration in this layer, and then it diffuses further in this solid phase. If the mass transfer takes place from this to the bulk of fluid, the trend will be opposite. So it will be like this, and then here could be like this. So this will be just changed to here. So will be initially this will be like this, and you reach this boundary here, then you have like this, and then constant like this. So at steady state, we'll have Ca0, this one, and CSR constant. If we assume steady state, the concentration here and the concentration here will not change. Okay, so the gradient force is constant. The gradient force is Ca0 minus Cas. At steady state, this gradient force is constant. At the thickness of the boundary layer, where you have Z equal del 0 here at the interface between the fluid and the solid surface, if we take or do balance on this line here, we'll have material coming back because of the convective mass transfer, and the convective mass transfer is Kc times Ca0 minus Cs. This is the gradient for the convective. So this is just driven by convective mass transfer. And then you have diffusion or molecular diffusion inside the solid, and you can write it as minus DAB times dCA over this Z plus CAV. Okay, and B is the material of the solid material, the solid surface or the porous solid. So if you have no accumulation, if the process is steady state, no accumulation here, the concentration will be constant throughout. Concentration here is constant, and therefore the N to the surface, to the solid, will equal the N to the boundary layer or the hydrodynamic layer. So you can equate them, and then if you, for example, interested in finding CAS, okay, you can also, this one also you can do the integration as we did in chapter 24 from CAS up to the C you want or the location you want here. So if this one is unsteady state process inside, then you can also use the charts that we did in chapter 25. Sorry. Okay, so in this chapter and the chapters to follow, we will be using Kc, and Kc is function of the properties of the fluid. So if you remember from chapter 22, when we evaluated the diffusion coefficient, DAB, for example, it was function of just the pressure, temperature, and molecular weight of the diffusing gas and the diffusion medium. If we talk about the diffusion in liquids, then it will be also function of the viscosity, but not other properties. Okay, here you will have also other properties affecting the Kc, as we will discuss later on, and also the dynamic characteristic of the flowing fluid. There we didn't mention anything about the dynamic characteristics, because the mass transfer or the diffusion is just based on natural tendency for the molecules to transfer from higher concentration to lower concentration. But here, okay, we have dynamic. We have something pushing the components or the molecules to transfer, which is the velocity, for example, the velocity gradient and the concentration gradient. Also, geometry here affects. Okay, in chapter 22, we didn't mention anything when we discussed the diffusion coefficient about the geometry and whether you have the mass the diffusive mass transfer taking place in rectangular coordinates or cylindrical or spherical. We still used the same DAB, the same diffusion coefficient, but here no, Kc will depend on the geometry. If you change the geometry, Kc will change. In this chapter, we'll be discussing two scenarios. The first one using dimensional analysis coupled with some experiments to evaluate Kc. So this is just to evaluate the diffusion coefficient, convective mass transfer coefficient. So this is the first treatment or the first analysis we will do. And the second analysis is the exact boundary layer analysis. Both will be discussed in this chapter in details to find the convective mass transfer coefficient. And there's also approximate boundary layer analysis. This will not cover it in detail. We'll just take the formula because we'll need the formula. The analysis there a little bit more advanced for your level, so we'll not go through the analysis, but we'll take the formula because we will need it. And the last part of this chapter is analogy between momentum, energy, and mass transfer, and we will not cover this part. In chapter 28, we'll discuss how to find the convective mass transfer coefficient for some geometries under laminar and turbulent flow. The geometries we will discuss will be flat plates, single spheres, single cylinders, flow through pipes, weighted wall column, packed and fluidized beds, and stirred tanks. So this will be covered. The correlations to estimate the convective mass transfer coefficient for these geometries will be discussed in chapter 28. Okay, so now let's start with some concentration boundary layer, which is somehow similar to the analysis you did in CH204 fluid mechanics. So let's say that we have this one, okay? This surface, this solid surface, and you have fluid flowing over this solid surface. As you know from fluid mechanics, you will have the hydrodynamic boundary layer. So the velocity at the surface using the no-slip boundary condition. You know what the no-slip condition?
Yes, the velocity at the surface is 0.
Yeah, the velocity at the surface is 0. So here you will have at y equals 0, if we take this point as y0, and this is the direction of increasing y, and this point is x0, and this is the direction of x, increasing x. And also you will have another dimension like this is for z, but let's do it just for 2 dimensions, y and x. So at y equals 0 at the interface here, or the surface of the solid surface here, the velocity will be 0 using the no boundary condition, or no slip condition, sorry, no slip condition. So along whenever y is 0, you are on the surface, and there will be no velocity regardless of the value of x. So for all x, when you talk about y equals 0, the velocity will be 0 based on the fluid mechanics concept you studied in CHE204. Then once you move up from the surface, the velocity will increase in both x and y. So if you take it from here, for example, okay, the velocity will increase in y. So if you take it from here, okay, like this one, for example, this is the velocity in x direction, but also if you go up, this is the velocity. So the maximum velocity will be in the center line. If this is like a duct, then will be in the center line. If it is a pipe, it will be in the center line of that pipe. That is the maximum velocity. And then you have the hyperbolic curve for this one. And the concentration, so our interest is in the concentration boundary layer. So at this point, if we have mass transfer taking place from the solid to the surrounding, we'll have CA equals CS on the surface here. And then CA, will call it C infinity in the fluid, bulk of fluid. This doesn't mean that it is large, but this means infinity means far from the surface. Okay? On the surface we use CAS, far from the surface. In the bulk of the fluid we call it CA infinity. And the velocity also we call it V infinity. It's not, doesn't mean that it is large, means just far from the surface. And the layer from here to here, okay, is delta. So the thickness of this hydrodynamic boundary layer is delta, and delta is changing. If you take it here, it will be different from here, different from here. So let's look also into this system before we start. So at the beginning, before the fluid flow starts, you will have, let's say the face here is stagnant. Okay, the face is stagnant. Then you start pumping the fluid, for example, you will have something developing like this. So the boundary layer hydrodynamic boundary layer will develop, and also the concentration boundary layer will develop. So if, let's say, the surface or the solid surface here is immobile, means it's stagnant there, you will have, you see that we have boundary layer here. Of course, the thickness of the boundary layer will increase along x. As you increase in x, the thickness will increase. So the thickness, this boundary layer will always exist. Okay, so it is there, but if under certain conditions, basically when you have very high velocity for the fluid here, it will be very thin. So it can be extremely thin, almost doesn't, or is near to not existent there. So it can be very, very thin depending on the fluid flow above the surface. Okay, so we will have in this layer, in this hydrodynamic boundary layer, we'll have, or the concentration boundary layer, we'll have some molecular mass transfer. So molecular mass transfer will always present in this layer here. Okay, so yes, the process is convective process because you have fluid flow, but in this layer, you will have also diffusive mass transfer taking place there. Okay, so if the fluid flow here, like this one above the boundary layer, is laminar, then we expect that the thickness of this layer will be quite significant compared to if the fluid is not laminar. So we'll have some, the layer here will increase if depending on the flow. And if the flow is laminar, you expect that you will have molecular diffusion here dominating. If the fluid flow is turbulent, yes, Abdulaziz. If the fluid flow is turbulent, okay, as you know from fluid mechanics, you will have eddies, and the eddies will move the material physically. So they just detach the material from the surface and move them physically with them. In that case, convective mass transfer will be dominating the mass transfer. So if you want to increase the mass transfer rates, okay, you have to increase the turbulency of the flow here. So with increasing the turbulence of the fluid flow, you will create more eddies, and you will detach the material, the liquid from the surface, and you will thoroughly mix the liquid with the eddies, and therefore you have effective and more higher mass transfer rate, and therefore you will have also higher convective mass transfer coefficient. So for the convective mass transfer coefficient will be higher with increasing, or will increase with increasing the velocity of the fluid. Okay. Let's yes.
معلش بس ايش المقصود بالباوندري لاير بالضبط يعني؟
Boundary layer, didn't study انت 201 204؟
مو بذاكر ايش المقصود بالباوندري لاير صراحه.
ذاكرت شباب you seen it in chapter in CH 204.
يمكن يا دكتور انا ما ادري والله، بس اقصد ممكن بس تذكرني بس.
خلينا نشوف الشباب. حد مر عليه الترم باوندري لاير؟
Yes, doctor.
Yes, doctor.
Yeah, if you didn't study it in 204, it will be a shock for me. Okay, 204 is all the course dependent, most of the course dependent on the boundary layer. So if you don't study the boundary layer in 204, I don't know what you studied then. So
يا دكتور نسيتها.
So for the yeah, I'll explain it for you, but you have to keep in mind that whatever you covered in the previous courses, you should know it, or you have to review the course material then. So the boundary layer is, if you have two phases, this is like fluid phase, maybe liquid or gas, and this is solid phase. And the solid phase is immobile, so it's not moving with the fluid, or maybe moving but at much slower velocity. Because of the no slip condition we mentioned, the velocity here will be 0. And then because of the cohesive forces between the molecules of the fluid, okay, these molecules here, the layer of this molecule on the surface will be, the velocity will be 0. The layer above them, the molecules above them, will be moving, but these molecules here try to drag them down, not allowing them to move. So their velocity will be less. And then will be another layer of molecules above this layer, and also this layer try to minimize or drag these molecules and slow down their velocity. So you'll have gradient in the velocity as you go up. As you go up, the velocity will be higher until you reach the center line here. If you have a pipe, this will be the center of the pipe where the velocity is maximum. Then you'll have this part is similar to this part. We'll have another layer here where the velocity is 0. So the boundary layer means that, okay, when you have solid and fluid in contact, you will have a layer of liquid here that is immobile, same as the surface, and this will affect the movement of all other molecules above them until you reach the center line when you get the velocity. So there will be, in other words, there will be velocity gradient in because of this no slip condition, and you will have a layer like this. We call it in fluid mechanics, we call it hydrodynamic boundary layer, because of the no slip condition and because of the cohesive forces between the molecules. The velocity, this layer will have different velocity. Okay, so we call it a boundary layer. And mainly this is for laminar, because if you have turbulent, there will be eddies. This will not be existent like this. So you will have velocity changing with y, okay, with y, and you will have something like this. Okay, this is the layer. This is the layer. Okay, and in this layer you will have different velocity as you go at different points. Okay.
ممتاز يعطيك العافية. معذرة.
So now we have this example here. This is a solid surface. Okay. We have solid surface here, and this one here. Okay, the black one here, and then on this solid surface we put a solvent coating or solvent with solid material. So we use a coating of something called photoresist polymer. And this polymer is dissolved in a volatile solvent, which is methyl ethyl ketone, MAK. So this is the solvent, and the solid material in the solvent is polymer. The coating covers this one here. The coating covers 15. This one, the thickness of the coating is 0.25 millimeters. So the thickness from here to here is 0.25 millimeters. And then you have this one like a table where the width and length of the table is 15 centimeter, and it is silicon material. Okay, so it's silicon wafer with this length and width 15 times 15, so it's like square, and the depth or the thickness of the coating is 0.25 millimeter. The wet coating contains, so the coating we use, which is the polymer plus the solvent, contains 38% polymer, is the solid material, and 78% solvent. So it's a mixture of solid and liquid. The total mass loading of the coating is this. So the total mass of the polymer, the solid polymer plus this liquid solvent is 0.5 gram. The solvent can be considered to be in a liquid state. So we can like say that this will be like a gel, but we can say that the polymer stays as solid and the solvent is liquid. The solvent will be evaporated. So we want to evaporate the solvent and keep this coating of the polymer here. So we just want to leave the coating, the thin coating of the polymer on the surface after we evaporate the solvent. So the solvent will be evaporated from the polymer surface by flowing air. So there will be air flowing here on the top of the plate, where the solvent will evaporate to the air. The solvent vapor must transfer from the coating surface through the hydrodynamic boundary layer. This is the hydrodynamic boundary layer above the surface, formed by the airflow over the surface. During the solvent evaporation process, a heating plate beneath the vapor maintains the coating at a uniform temperature of 27. So the temperature in the coating material is kept constant at 27 degrees Celsius. And the vapor pressure exerted by the solvent at this temperature is constant at 99.4 millimeter mercury. Because the solvent is volatile, okay, and as you know from CH2O1, any volatile component will evaporate at any temperature. Of course, the evaporation will depend on the temperature. The higher temperature will have more evaporation, and therefore we call it the vapor pressure. Okay? The vapor pressure at just adjacent to the surface here. So that is the maximum partial pressure of the solvent in vapor phase compared to the total pressure. So the total pressure, okay, or the air flowing here is at also 27 degrees Celsius, so same temperature, and total pressure of 1 atmosphere. The rate of solvent evaporation is limited by convective mass transfer process. So you will have the solvent diffusing through the coating layer, and then once it reaches here, then it will transfer by convection. And in this bulk of air, the concentration is constant. We'll come to it later. So the diffusion in the coating is fast compared to the convective mass transfer. This is what we say the rate of solvent evaporation is limited by convective mass transfer process, because we'll say that CAS here should be constant. Otherwise, the process to this, the transfer of this one, or there will be concentration gradient here for CAS. Or the CAS will depend on time. But it's mentioned here that the vapor pressure is constant. The vapor pressure constant means that CAS is constant. So the rate of evaporation is limited by convective mass transfer process. The flow of air is high enough that relative to the rate of solvent transfer, the concentration of solvent vapor in the bulk gas Ca infinity is very small and can be assumed to be 0. So because the air is flowing very fast here, so every like fraction of second, you just bring new air, and the new air doesn't contain MEK, so it's pure. Since the flow is fast, okay, so this is almost coming pure, and then you're evaporating very little of the solvent here. So the concentration here, basically evaporating very small amount to a large quantity of air that is flowing fast. So we can assume that Ca infinity is 0. So the concentration of A in the bulk of air is 0. Furthermore, any resistance associated with the molecular diffusion of solvent through the very thin polymer coating can be neglected. Remember that we said we have here in this boundary layer, always the molecular diffusion exists. Mass transfer by molecular diffusion exists in this layer, okay, as mentioned in the previous slide. But based on this assumption, okay, we assume that the resistance associated with molecular diffusion to the solvent through the very thin polymer coating, okay, can be neglected. Okay, so, and also we assume that here is dominated by convection, and based on what we discussed in chapter 25, we'll have two resistances, resistance here and resistance in the solid. So the resistance in the solid based on this assumption is negligible. So just the resistance lies in the boundary layer. Experimental tests demonstrated that the solvent in the polymer coating evaporated after 45 seconds. So the total time for the process to evaporate all the solvent is just 45 seconds, okay, after we flow the air. Based on the assumptions above, what is an estimate of the convective mass transfer coefficient needed for this process? So what is Kc? The molecular diffusion, the molecular weight of MAK is 72 gram per mole. Okay, so as you say, it's very long description, but all these are what you need is the in bold here. Okay, some of these assumptions are helpful. We cannot solve without them. So we need basically to find Kc. Okay, so what is Kc for this process? Yes, Shabab.
Doctor, isn't the statement that it's dominated by the convective mass transfer is the same as that there is no resistance in molecular diffusion?
Yes, yes, they are similar. Yes.
So if we write assumptions, we only write one of them.
If we say that, where is this? Is any resistance associated with the molecular diffusion of the solvent through the very thin can be neglected. This is similar to this one. The rate of solvent is limited by convection. So they are almost serving the same purpose. Yes. Okay.
Okay.
Doctor,
Okay. So, yes.
sorry, is this the second case, solid flow contacting fluid?
This one here.
Yes.
Yes, somehow similar to this. Yeah, similar to this, but opposite to this. It's not adsorption. It's just like you evaporating something. Okay, so somehow similar to the evaporation, but it's gas and solid, not gas and liquid. Okay, so the case here, fluid contacting a solid surface, okay, can be where the solid acts as a source. This is also similar to the case. So we have the solid is serving as the source for A. And also you can say it's similar to this, but you replace the liquid with solid. Okay, and you evaporate the solvent. What I mentioned that we will not cover this part, that we will not have adsorption. Okay, you will not have adsorption, so that the solvent will not, or the solute will not transfer from this fluid and stays on the solid. Okay, but if it is evaporation, we will cover it because somehow it's similar to this. And it's basically similar to this, but the direction is the opposite. Okay. Okay, so let's start with doing mass balance. Okay, because now if you look at it, we have the solvent here initially, and then it evaporates and go to the bulk of air. And we said that the pressure, the vapor pressure there is constant. So the vapor pressure here at the interface between the fluid, the airflow, or the fluid air, and also the solid material here with the solvent is constant. So CAS will be constant. So means that no accumulation at the interface here. Otherwise, CAS will change in time, but we said it's constant. So means that you have the process inside this one is unsteady state, but in this bulk is steady state, okay, because you have no accumulation here. So if you do balance on the layer here, you will say that this is the general mass balance, input minus output plus generation minus consumption equal accumulation. This is on the coating here, on the coating. So for the coating, we don't have any input because A leaves the coating, doesn't enter the coating. And there's no reaction, so these two terms, generation and consumption, are zeros. So we have minus output equal accumulation. Again, we are talking about the coating here. So if you take also this point here, so the balance on the coating gives us this equation, okay? This one, minus output equal accumulation. But I will also, if I do balance on this just point here, the interface, since there's no accumulation, input to this point will equal output. And the output is basically the convective flux, okay? Convective flux. So this is the output at this point, which is the output from the layer. So we can say that the output from the coating is equal to the convective flux. And we'll use the Kc later on here. Okay, Kc times CAS minus C infinity. This is the convective flux we will be talking about. So this is the balance minus output equal accumulation, and this is in mass. This should be also in mass. So Na, which is the convective flux leaving the coating, times the surface area perpendicular to the mass transfer, times the molecular weight of A. Okay, this, as you know, is mole per meter square, for example, per time. You multiply by surface area, it will be mole per time, and this is mass per time. So mole per time, you have to multiply by molecular weight to change it into mass per time. So in the note and also in the textbook, correct this equation, should be Ma also here. So please correct it. Okay. So molecular weight you multiply this NaS times the molecular weight, and also here you multiply by Ma. So this is output, and this is minus because of the minus sign here, equal dMA over dt. And we can integrate, since we assume that CAS is constant, and CA0 is also, CA infinity is 0 also and constant, and Kc is constant, convective mass transfer coefficient. So the flux will be constant because Kc is constant, Ca is constant, Ca infinity is constant. All these constants, when you multiply constant quantities, you will get also constant. So Na is constant, and the surface area is also constant, so you can take them outside the integration. Also the molecular weight is constant, and integrate, so multiply both sides by dt here, so you will have dt, and this will be dMA. Integrate from 0 to the T final of the process, and from the initial mass till the end of the process. At the end, we'll evaporate all the solvent. We're doing the balance on the solvent in this coating. So all at the end of the time, T final, we'll have all the solvent evaporated. So the remaining material or the remaining solvent in the coating will be 0. So this simple integration, do them. So this will be from 0 to T. So we'll get T final here minus 0. So it will be T final. And this will be minus Ma0. And then you divide, so you'll have minus here, minus Ma0, and this will be minus. So the minus will cancel, and you have Ma0 equal Na times Ma times S times T final. So you get Na equal Ma0 over Ma Tf plus times S. The molecular weight is given is 72 gram per mole. The time for the process is 45 seconds, as given here, 45 seconds. And the surface, okay, we know that it's like a table or wafer with length of 15 centimeter and width of 15 centimeters. So the air flowing on this area from here to the other side is 15 centimeter, and the length is 15 centimeters. So the area perpendicular to the flow is 15 by 15, which is 225 centimeters square. Then you get the flux. The flux will be 4.8 times 10 to the 1-7 mole second centimeter square. And you know that the flux is also equal Kc times Cas minus C infinity, because here, as according to the assumption, the flux is just by convection. Yes.
Why did he multiply by 0.7 the mass?
We'll come to that. We'll come to that. Okay, so this one you mean this one?
Yes.
Because of this. How much solvent in the coating?
Okay.
Not all the coating is solvent, just solid, and the solid doesn't evaporate. What evaporates is the solvent, which is 17% of this number. Okay, so now we said that Kc, or the mass transfer in this layer, is dominated by the flux, the convective flux. So it will be just N equal Kc times the concentration gradient, which is Cs minus Ca infinity. Based on the assumption that we have very high airflow and it's pure, therefore Ca infinity is approximated to be 0, and Cs we can find from the partial pressure of the solvent at the surface. So Cs equal the vapor pressure, sorry, which is PA, the vapor pressure of A over RT, assuming ideal gas law, assuming ideal gas behavior. So this is given, partial pressure, vapor pressure is given as 99.4 millimeter mercury, and the total pressure is 1 atmosphere, which is 760 millimeter mercury. So you get CAS equal 5.31 times 10 to the 1-6 mole per centimeter cube. C infinity is 0, so you sub here, and then you'll have Na equal Kc times Cs. Cs is known, Na is known. You just divide Na over Cs, you get the Kc. So Kc will be Na over Cs minus C infinity, and C infinity is 0. Kc, Cs is from here. You get 0.09 centimeter per second. So the value of Kc is 0.09 centimeter per second. Okay, now this, as you say, depends on the time for the process, because you divide here, so you get the flux. Depends as you increase the flux. If you see is constant, so if you increase the flux, Kc will increase. In diffusion, this is not the case. The AB is independent of the flux, but Kc depends on the flux. So if you increase the time, okay, here the Kc will this will be less. If you shorten the time, this will be high, and also depends on the surface area. If this one is high, then you will have this is small. If it is small, this will be high, and also the amount, the initial amount. So Kc is function of all these: the mass you put initially, the time, the surface area, and also, okay, this will depend on the flow, because if you increase the velocity of air, you expect that to evaporate this one faster. The coating here is faster. So that will also depend on the velocity, as we will see later.
Doctor,
Yes.
did we use here a steady state process? Because the concentration are constant, right?
Steady state for this the balance from here to the other layer. So at the surface here we have constant Cas, and this is constant. So you'll have steady state process here. But inside this coating is not steady state, because you have something, the mass is decreasing. So if you do balance on the coating here, no, it's not steady state, because the accumulation of the solvent in the layer changes. It was 0.35 in the beginning, then it will become 0 at the end. So on the coating, no, it's not steady state. But from this layer here at the interface, yes, it is steady state. Okay.
Yes, doctor.
Okay, so we'll stop here, and next time we'll continue from this point. Just to save time, I'll stop, and if you have questions, you can ask after that.